An 844-foot, 40,000-ton amphibious assault ship survives by compartmentalization, redundancy, and disciplined damage control. But when the USS Bonhomme Richard sat tied to Pier 2 at Naval Base San Diego, a $250 million modernization project had heavily degraded the watertight boundaries, detection coverage, and firefighting readiness that normally isolate internal hazards. In a combat zone, a localized fire or kinetic strike is supposed to meet a series of controlled steel boundaries. The ship takes the hit, the bulkheads and closures slow the spread, and damage control teams attack the isolated sector with water, foam, or other installed systems. The geometry of the ship is one of its primary weapons against disaster. But in a shipyard environment, that foundational survival logic is completely inverted. To route miles of new electrical cables, upgrade combat systems, and install heavy aviation equipment, engineering crews must break compartmentalization in controlled, physical ways. Heavy watertight doors designed to seal instantly during an emergency are pinned open. Armored hatches are propped wide to accommodate massive temporary ventilation hoses, high-voltage power lines, and welding equipment. The impenetrable steel grid becomes a massive, interconnected cavern. The ship is deliberately wounded to allow the upgrades to proceed. The Bonhomme Richard was a dormant giant undergoing critical upgrades to handle advanced strike aircraft. Fixed suppression coverage for key machinery, vehicle, and aviation-related spaces was degraded, isolated, or unavailable, leaving early response dependent on manual action. Heat detection and alarm coverage was also degraded or isolated in places, reducing the chance of a clean, immediate warning when smoke first appeared. The vulnerability went much deeper than deactivated sensors. The core of a ship's manual firefighting capability relies on an extensive network of internal fire stations, which provide high-pressure water access across every single deck. On the Bonhomme Richard, 87% of the internal fire stations were placed into an inactive equipment maintenance status. This meant that even if a crew located a fire, the immediate hoses and valves at their disposal were dry, disconnected, tagged out, or completely dismantled. The physical environment compounded this severe tactical disadvantage. The decks and passageways were littered with combustible scaffolding, temporary wooden staging, cardboard packing materials, and industrial trash. With internal water access disabled and combustible staging materials crowding the decks, the vessel became heavily dependent on a small skeleton crew of sailors. Deep inside the lower hull, below the massive hangar areas, sits the lower vehicle storage area. Known operationally as the Lower V, this cavernous space is designed to hold heavy marine expeditionary equipment, armored vehicles, and large cargo loads. During a major shipyard maintenance availability, an empty Lower V can become a deep staging ground and a repository for bulk supplies. On the morning of July 12, 2020, smoke and fire were first reported in this lower compartment. In a fully operational, battle-ready warship, a sudden fire in a vehicle stowage area would normally trigger a coordinated damage control response built around boundaries, hose teams, and installed suppression where available. On Bonhomme Richard, the response began inside an open maintenance environment. Directly above the deep V, open armored deck hatches gave heat and smoke a vertical route. The thick, temporary utility cables snaking vertically through the decks provided a continuous, uninterrupted pathway for rapid heat expansion and toxic smoke. The compromised industrial architecture gave the fire a continuous, unobstructed labyrinth of open air and concentrated combustible material. Initial response forces entered a massive, dark lower deck maze with no immediate water pressure. The initial spark was contained deep in the bottom of the hull, but the compromised industrial architecture of the warship guaranteed it would not stay there. At roughly 1200 to 1400 degrees Fahrenheit, the interior of a warship enters a punishing thermal regime where aluminum alloys can soften, sag, or melt, and steel can lose strength, warp, and transmit heat into spaces that have not yet seen open flame. Once a heavy fire takes hold inside a modern warship, the vessel rapidly ceases to be a ship and becomes a massive steel oven. Heavy steel bulkheads and thick outer hull plating are incredibly efficient at trapping and reflecting thermal energy inward. As the fire burned continuously, the trapped thermal mass compounded. Sensors and thermal imaging indicated that parts of the ship reached staggering extremes, soaring into the 1200-degree range and, in some reports, higher. At these temperatures, the fundamental physics of naval architecture become a lethal liability. Modern amphibious assault ships use a careful weight management logic. The lower hull, major decks, and heavy structural foundations rely on steel, while upper structures and fittings may include lighter alloys and components to reduce top weight. That material balance matters because every pound carried high above the waterline affects the ship's center of gravity and its stability margin in rough seas. However, aluminum alloys carry a critical thermal weakness. Long before they become liquid, they can lose a large share of their strength and stiffness. Steel can also lose load-bearing capacity under severe fire exposure, but aluminum-rich components generally weaken much earlier, and common aluminum alloys can enter their melting range near the 1200-degree Fahrenheit band. As heat radiated upward through open compartments and vertical pathways, it baked the upper structures from the inside out. Aluminum-rich components and other heat-sensitive fittings warped, sagged, and failed as the fire attacked the command spaces and the island area. The forward mast, an extremely heavy external structure loaded with radar arrays, communication antennas, and sensor equipment, lost critical support as the surrounding structure was compromised. Unable to carry the load safely, the mast collapsed downward into the damaged upper structure. This massive external collapse became an unmistakable visual signature of the thermal violence tearing through the ship's superstructure. Internal damage control teams were entirely blocked by this radiating wall of heat. Human survival in a 1400-degree environment is physically impossible, regardless of protective equipment. To slow the destruction of the remaining upper structures and cool the exterior flight deck, command turned to an extraordinary aerial firefighting support effort. A continuous rotation of Mike Hotel 60 Sierra naval helicopters was deployed over the active naval base. Operating in thick smoke, heat, and turbulent air, the flight crews began a massive series of water drops intended to cool the superstructure and flight deck, so internal crews could keep fighting the fire. The approach demanded precise flying above a burning warship inside an active naval base. The crews carried heavy suspended buckets, cycling to scoop seawater from the bay before returning over the damaged island, superstructure, and flight deck. This aerial assault was not a short operational burst. The flight crews executed over 1,500 individual water bucket drops. Each pass bought time for crews below. By continuously pounding the exterior superstructure with cold ocean water, they attempted to forcefully bleed off the massive internal heat before the entire upper half of the ship suffered total structural failure. The sheer scale of this continuous aerial bombardment turned the pier into an aggressive three-dimensional combat zone. The staggering volume of dropped water temporarily fought back the thermal expansion, cooling the outer skin of the ship. Yet the most dangerous heat still rose from below. The architectural design of an amphibious assault ship includes a massive hangar bay, creating a vast operational void inside the steel hull. When that space is tied into maintenance openings, the geometry can shift from a controlled staging ground into a dangerous pathway for heat and smoke. In an intact warship, closed steel decks and boundaries slow upward heat movement. Inside this compromised hull, the lower vehicle storage area had pathways that allowed heat, smoke, and flame to move toward the hangar and surrounding decks. This layout created chimney-like effects that accelerated vertical fire spread. As the heat expanded deep inside the ship, the fire drew fresh air through available openings and pushed smoke and flame upward through the same maintenance pathways that had made the modernization possible. The hangar bay became a vast smoke and heat reservoir. The fire did not simply crawl from room to room. It exploited open boundaries, temporary utilities, and ventilation paths, jumping levels faster than a normal compartment-by-compartment fight could contain. The crew now had to fight a fire moving vertically, not compartment by compartment. Stopping a vertical inferno requires an overwhelming internal human assault. Federal civilian firefighters and a massive rotating force of 400 sailors aggressively pushed back into the dark, toxic labyrinth to hunt the flames. Inside, thick smoke swallowed handheld flashlight beams while industrial debris and tangled maintenance lines turned basic navigation into a hazard. Because most of the internal fire stations were unavailable or degraded, damage control teams had to stretch heavy, charged hose lines from available shipboard, pierside, and external water sources deep into the bowels of the ship. Advancing a charge line through narrow, slanted passageways over temporary scaffolding requires extreme physical force. The physical strain meant that individual hose teams could only survive at the front line for roughly 10 to 15 minutes before their air ran low and core body temperatures spiked. Fresh teams took over from exhausted crews, dragging lines forward foot by foot in absolute darkness. Despite this incredibly aggressive and heroic internal push, the chimney effect drastically outpaced the human effort. The aggressive vertical draft actively fed the flames, pushing the inferno directly into critical spaces like the Combat Information Center, crew berthing quarters, and vital mechanical rooms. Heat conducted through the steel boundaries could preheat nearby coverings, insulation, and stored combustibles, until adjacent spaces became ready to flash or ignite even without direct flame contact from the original fire. This rapid expansion meant the teams were constantly flanked by the shifting inferno. By the end of the violent progression, the fire completely gutted 11 of the 14 decks of the warship, systematically hollowing out the interior of the vessel. The scale of the damage forced the firefight toward containment. Internal crews could no longer offset the heat alone. That shift increased reliance on external water volume, but pumping an unending supply of heavy liquid directly into the top of a floating steel structure sets a terrifying physics trap that will violently threaten the survival of the entire hull. The trap began as continuous internal hose lines, tug streams, and aerial bucket drops delivered hundreds of thousands of gallons of water into the ship. The water was necessary to fight the heat, but every gallon added mass and every gallon trapped high in the superstructure, hangar areas, and upper levels reduced the margin of safety faster than normal drainage could relieve it. The firefight had opened a second front. A heavily armored naval vessel maintains its upright posture in the water by relying on a strict relationship between its center of gravity and its center of buoyancy. The heavy steel hull and the massive internal machinery spaces are located deep below the waterline, pulling the center of gravity downward and acting like a massive keel. This extremely low weight distribution creates a natural righting arm. If the ship rolls to one side, gravity simply pulls the heavy bottom back down, returning the vessel to a highly stable, upright position. But naval stability is not a static condition. It is a highly sensitive mathematical balance that can be completely destroyed by adding massive top weight. As suppression water pooled high inside the gutted upper decks, the accumulated weight reduced the ship's stability margin and weakened the righting forces that normally resist a dangerous list. But the true danger was not just the weight of the water, the true danger was its mobility. The water was not safely contained inside secured internal holding tanks. It was actively pooling across the massive, open expanses of the hangar bay and the heavily blackened upper vehicle decks. This created a highly lethal fluid dynamic known as the free surface effect. When a large body of unrestrained liquid rests on a wide, flat deck, any slight movement of the ship causes the entire mass of water to violently surge toward the lowest point. As the heavy liquid rushes to one side, its crushing weight transfers entirely to that edge, aggressively forcing the ship to lean further. This creates a terrifying physical feedback loop. The more the ship leans, the more the water violently cascades to that side, multiplying the overturning force with every single inch of downward movement. Under the crushing influence of this free surface effect, the warship began to face a second disaster. The massive hull developed a dangerous list as water collected inside compartments and shifted through damaged or open spaces. Firefighters and stability teams had to treat the ship not as a fixed steel platform, but as a moving, wounded hull with thousands of tons of water changing its balance. Each shift in list forced crews to pull back, reassess, and coordinate firefighting with stability control. A 40,000-ton ship with an uncontrolled list is not merely damaged. It is moving toward the edge of a stability failure. The stability crisis had reached a critical threshold. The ship was no longer simply burning, it was listing. The risk was no longer theoretical. Alongside the pier, that failure would have been catastrophic. The water required to kill the massive fire was now also threatening the survival of the hull. The operation faced an absolute paradox. The damage control teams could not simply stop applying water, or the intense thermal energy would keep destroying the ship. But every additional gallon trapped inside the upper decks pushed the vessel closer to a catastrophic stability failure. The warship was leaning toward its breaking point, demanding immediate engineering action to control water, weight, and list. The stability paradox forced an engineering response beyond suppression. That response began with trapped water. The first critical step was emergency dewatering. Water trapped in upper and internal spaces could not simply disappear through normal drainage paths. Heat damage, debris, temporary services, and closed or obstructed boundaries held large pools of water inside the ship. Teams and support contractors worked to rig pumps, route hoses, and remove water continuously from flooded compartments. This mechanical dewatering effort was essential to keep the added weight from worsening the list. At the same time, stability personnel monitored the ship's attitude and managed the hull as a floating structure, not just a burning building. The work demanded constant coordination between internal crews, pierside responders, tug support, and command teams watching the ship's movement from outside. Their stability work did not erase the damage, but it kept the hull available for continued suppression. When the final flames died, Bonhomme Richard was left as a cold, gutted steel shell awaiting the next calculation. The decision to save or abandon a heavily damaged warship ultimately relies on a brutal mathematical trade-off, weighing $3 billion of reconstruction capital against the physical reality of dead steel. When engineering assessments began, structural surveyors did not measure operational intent. They measured whether the damaged metal, frames, and foundations could ever be trusted again. Sustained fire can leave structural steel warped, uncertified, and unsafe until detailed inspection proves otherwise. It is the combined reality of heat distortion, lost material certification, corrosion, water damage, smoke contamination, and hidden damage inside critical foundations. To repair a vessel in this heavily degraded state, naval architects cannot simply weld fresh plates over the blackened interior frames. Industrial crews would have to inspect, cut out, and replace enormous sections of compromised structure, wiring, piping, ventilation, and machinery foundations. The repair would become a shipbuilding scale reconstruction inside the burned hull. That level of deep structural replacement carried a staggering logistical and financial penalty. Restoring the ship to its original configuration was estimated at between $2.5 and $3.2 billion, with a 5 to 7 year repair timeline. During that span, shipyard capacity, labor, and specialized planning would be tied to one burned hull instead of the active fleet. The engineering and acquisition boards investigated alternative operational paths. They analyzed the feasibility of cutting away damaged upper structures and converting the surviving hull into another type of support ship, such as a hospital ship, tender, or command and control platform. Even a conversion would require years of work and more than $1 billion while producing a compromised result built around a deeply damaged hull. Navy leadership judged those missions better served by new alternatives, not by forcing a burned amphibious assault ship into a second life. The massive damage had pushed the warship past the economic point of no return. Following this rigid operational logic, the United States Navy officially decommissioned the massive vessel. Heavy salvage teams systematically moved through the lower, unburned spaces, aggressively harvesting salvageable mechanical parts, intact watertight hatches, and viable sensor arrays to serve as spare parts for the rest of the active fleet. After the salvage sweep, the hull was prepared for tow. Commercial ocean tugs pulled it out of San Diego, down toward the Panama Canal route, through the canal in May 2021, and onward toward Brownsville, Texas. The disposal path was publicly estimated at about $30 million for the overall effort, while the later ship-breaking transfer itself was reported separately at $3.66 million. The hull entered a heavy cutting slip. Industrial mechanical shears and high heat cutting torches attacked the exterior plating. Steel walls were sliced into manageable rectangular sections, lifted away by machinery, and dropped into waiting barges. Heavy lift cranes tore internal bulkheads away from the lower keel, exposing the lower vehicle storage area one final time. After usable components had been harvested for the fleet and the remaining hull delivered to the breaker, Bonhomme Richard was reduced from aviation platform to recoverable metal.